Okay, good afternoon, everyone. I'm Zhilu. I'm from NTU in Norway. So now you can see the topic of today is hydrogen enrichment in nickel alloys. Some insights. Is some insights from myself based on my own experience. But I think from the last presentation, it was really a comprehensive work that talks about the effect of precipitate and the beneficial of precipitate to reduce the hydrogen enrichment behavior. And my talk will be focused on the detrimental effect of those precipitates. Okay. My presentation consists of 3 parts. First of all, a preliminary background introduction, then the failure mechanism of different types of nickel alloys that are used in the oil and gas industries in Norway, and finally, conclusions and perspectives. So as what we heard from Professor Jianying He in the morning, she presented that nickel alloys are intensively used in the oil and gas industries in Norway. And it has been considered as hydrogen-resistant alloys. But after some time, we can see the first report of failure in 2003 on the nickel alloys. And afterwards, several failure cases occurred. First of all, it happened in 2019. It happened on the subsea clamp connector in the North Sea. This fastener was installed in 2003 and subjected to cathodic protection through contacting parts with a sacrificial anode attached. You can see this clear fracture, sudden fracture of the fastener. And after investigation, it was proposed that it's caused by hydrogen embrittlement. Another case reported in 2022 is clamped connector at the flow base C3 at the Bout field. It was installed in 1998, and it has been in operation for more than 20 years. And after that, a failure was reported on this alloy. It's alloy 725 drive screw. The cathodic protection potential was not present at the beginning, but after some time, there was a breakage of the coating on the surface, and then the material was directly contacted with the CP condition. And finally, this fracture happened. And now what's happening in the industry? So people are really eager to see what will happen the year afterwards. Are we still going to accept the use of nickel alloys, or should we totally ban the use of this alloy? So that's why in NTU and in collaboration with the Norwegian industry partners, we have 2 projects. The first one is AMPEAT, which has finished. And then the second one is ongoing, is microstructure-informed hydrogen embrittlement life prediction of nickel-based alloys, which is also a collaboration with the Professor Jianying He and Zhiliang Zhang. Now we can take a look at the failure mechanisms of the reported failed components. This one is alloy 716. This figure I think you already see from Professor Jianying He's presentation. Then we took a look at the zone A, zone 1, zone 2, and we see that a clear intergranular fracture of this fastener, failed fastener. And further investigation reveals the total intergranular fracture. That means the intergranular cracking is the main reason for the failure of this fastener. If we take a close look at the microstructure, we can see along the green boundary, many precipitates are present. Some of them are continuous along the green boundary, and some of them are in the acidic shape. And then these precipitates are carbides and recently reported as phase based on the results from XRD. Tensile testing results reviewed the same behavior. So we can see these tiny F phase are precipitates along the green boundary, and in the hydrogen environments, the interface between F phase and the matrix, they are fractured, and nanovoids can be observed. As you can see also here from the EDSD results, we can see the total intergranular fracture of this material. In-depth analysis by using tensile testing and as secondary electron image and BSE image also reveal the microvoids along the interface of this F phase and the matrix. You can see this is the bad guy we are looking at. Further, so we did a further DFT calculations, and we saw that there are 6 interstitial positions that are more stable in the interface between the F phase and the nickel matrix. And by introducing hydrogen, we can clearly see a trend that the hydrogen reduces the interfacial interaction energy, which is an indication of the bonding strength between the matrix and the F phase. And from here, you will see that once hydrogen are trapped at the interface, if they want to migrate to the nickel matrix or migrate towards the F phase matrix, then it has to overcome an energy barrier. And this energy barrier can be as high as 0.5 electron volts. And our conclusion is that those F phase and the nickel matrix interfaces are stable hydrogen trapping sites. So as previous presentation, we also see the coherent interface is a stable hydrogen trapping site. But those precipitates are in the matrix. So if they are present at the green boundary, it would be another story. And the dissolution of hydrogen atoms weakens the binding strength of the interface. Another example of the failure mechanisms that I presented on the this drive screw, if you remember, we did also tensile testing on this material. And then we take a look at the surface cracks. Here you can see these are intergranular cracks. And then what we see is that those interface has something inside. And this is not straight forward, so not straight, and it's zigzag morphology. After this SEM EDS, we saw that we have a layer of sulfur at the green boundary. And we believe it's the sulfur deposition that caused the failure of this drive screw. I still remember Professor Luo Hong also presented the sulfur deposition in high entropy alloys can be a detrimental effect. So let's come to the diffusion. We measure the hydrogen content from the surface of the drive screw towards the center, and we observe that hydrogen penetration depth can reach up to 4 millimeters. But if we take a look at the hydrogen diffusion coefficient in the literature and make a simple calculation, actually after 20 years, we only can estimate that hydrogen can penetrate inside the material for only 1 millimeter. So what was happening there? Why we observe such a large hydrogen penetration depth? Something must happen, right? So then we did a permeation test with the samples being loaded higher than the yielding strength, which means we load the samples to the plastic deformation condition, and then we study the permeation behavior of the nickel alloy. This is alloy 625. It has some green boundary carbides alongside, and we saw that when we increase the strain, we observed the cracking of those carbides, and definitely, besides the cracking of carbides, there should be something happening also along the other green boundaries, such as the vacancy formation that the other researchers proposed. And what we see is that the permeation or the diffusivity of the hydrogen when we screen the material is largely increased. So this may indicate that why we have such a high hydrogen diffusion depth And also, as you can see here, where we see the cracks, this is taken from the failed component. Those cracks always happened at the thread roots, where the stress concentrations are located. And there, in these areas, we believe that the local behavior of the microstructure shouldn't only go through yielding, maybe it's also beyond the yielding and reach through the plastic deformation. That's why we already have some breakage of the microstructure features, or we have already induced some vacancies, and those failures can promote the hydrogen diffusion, and so they kind of assist the cracking at these stress concentration areas. So that is tensile testing, right? Then what's happening in the compressive test? So we did in situ micropillar compression test in the green boundary. In the green boundary containing some carbides. These are carbides. And here, as you can see after the testing, actually, you can say that we slightly observe an increasing of the yielding behavior or the strength, but actually I wouldn't say it's a big like obvious phenomenon. And the surface also show that around these carbides, we see the narrow slip lines in the hydrogen case, but still I can't draw a concrete conclusion based on this study. But it indicates that in different loading conditions, we actually can observe different hydrogen enrichment behavior. So the conclusions and perspectives, hydrogen-assisted intergranular failure in the typically used nickel alloys that were used in the oil and gas industries in Norway is highly correlated to the green boundary precipitates and green boundary sulfur segregation. Those interfaces can be the stable hydrogen trapping sites, and the local high stress and plasticity-induced effects influence the hydrogen uptake and diffusion. So the future work, eliminate the green boundary precipitate is the first step to achieve a high hydrogen resistant nickel alloy. Nobody knows if this can be achieved, but still promising. Comprehensive testing and characterization methods are essential for ranking the hydrogen stress cracking resistance of nickel alloys, which means which technique should we use to select the proper material. And the predictive void-based model with green boundary precipitates is highly recommended. Thank you for the listening.